We didn't call it a predicate 0 of something, we just say x plus y equals 0. Again, for our needs right now, predicates just simply mean some property that happens. So you don't have to use a predicate, you can just state the property x plus y equals 0. This is false. The reason this is false is because the quantifiers don't work. This y now has to be global. When I say there is a y, I'm fixing the y. Now I can choose any y I like, but it's fixed in stone. So the reason is that y is global, does not depend on x. Right. So keep in mind that with those quantifiers, the key of understanding the statement and manipulating the statement and getting some insight into what you want to prove is understanding the dependency of the variables. Who depends on who? That is the key. And I won't insist on predicates, but you may have a problem that asks you state in predicate form something. That simply means take whatever property you have, create a Boolean form, you name it 0 or whatever you want, and then say this predicate of applying to something is true. And I could have written this predicate with 2 variables if I wanted. I could have another predicate 0 of x and y. This has only one argument. I could have another predicate that says this is true if x plus y equals 0 and false if x plus y is not 0. So now I state the same property, but with a predicate that takes 2 inputs. So in this case, how much is 0 of 1 and minus 5?
False.
That's false. I know some people make a big deal out of this, including some other instructors and books. It's not a big deal. It's just trying to write fancy a property that could be very easily stated in English words. Okay, so the exercise we had last time that I would like to get back to is what is the calculus limit definition of a sequence, right? So that's where we got ended. We say here's the sequence. Let's call it A1, A2, AN, and the sequence is infinite, right? And we have this definition of the limit. That's the calculus definition of the limit, right? So let's say the limit is y, or what do you say? It's x, I think, limit x. So we call it limit from n goes to infinity of an equal x, right? This is a notation, means what? Means that I think we say for every y that is positive, there is a n0, we call this starting point in the sequence. And for every n starting at n0, what was the mathematical property? Somebody was saying it last time, I need for the limit to work out. So for every, how we thought about this is, for every, here's my x, my limit. Y is the range of the interval, so it's from here to here. This is x minus y, and this is x plus y. So y is this chunk. N0 is in the sequence at some point A17 or A27 or A65. At some point in the sequence, after that point, what? What is the mathematical property that we need? Yes?
Every a sub n is in that interval.
Right. An is in here somewhere. So how do we write that? We can say An is between x plus y and x minus y. That's a way to say it's in that interval, right? Or we can say An minus x in absolute value is smaller than y. Because those two things mean the same thing. An's got to be between x minus y and x plus y. Yes?
So when you wrote that for all n greater than or equal to n sub 0, did you mean like for all n whose index?
Right, n are the indices of the sequence, right?
Oh.
So
yeah.
you see An here.
Okay, yeah.
So what this is saying, there is a starting index.
Okay.
starting, maybe if I call it index, it's more clear. And after that starting index, all the values must be in that interval. Right? So what's an example of this? Let's do a limit here. Let's say some number. So let's say an is 1 over n. So the sequence is then 1, 1 over 2, 1 over 3, 1 over 4, 1 over 100, so on and so forth, right? That's the sequence. What is the limit of this sequence? What is the limit, the convergence value? 0, right? So x equals 0. How that definition work out with the quantifiers? For every y that's bigger than 0, there is a starting point, and for every n bigger than that starting point, we have the equation, so a n minus x is smaller than y, which for us means, of course, if I translate this into my actual values, a n is 1 over n, minus x is 0, it's smaller than y. So then if I translate it further, this means 1 over n is smaller than y, because minus 0 doesn't do anything, and the absolute value, those bars on numbers means absolute value, right? They also don't do anything because the quantity inside is positive. How many people with me so far? So let's recap things so far. My limit for this sequence was 0. Therefore, I need for every interval, there is a starting point in the sequence. And after that point, the difference between the sequence value and the limit, which is 1 over n minus 0, in absolute value, but absolute value doesn't do anything because the inside is positive, smaller than y. So is this true? Now that's a definition, but is it true that for this particular series, the limit is 0, which means every time you pick a y, there is a starting point for which this happens? How do we prove such a thing? So in order to prove that this series converges to 0, we need to show that the property is true. Meaning, anytime somebody picks a y, I can find a starting index in the sequence starting from where this happens. You can think of this y as being your adversary. My adversary can pick any y it wants. Could be very difficult. My job is to show that for every y my adversary picks, I can find the n0, right? That's essentially what this property is saying in plain words. Everywhere you're given a y, you can find the n0 that has this property. If that's true, then the convergence goes to 0. The limit is 0. So what do we need to do to prove this thing? Y is given arbitrary. Y is bigger than 0. We have no control over it. It says for any y, so somebody picks the y, whatever y. We need to show that we can find the starting point in the sequence such that, so we need, I'm going to say want an n0 such that every n bigger than n0, this is a start index. We have the property 1 over n will be smaller than y. So how do we find the n0? Now, this property will be true if it's true at n0, if it's true also after n0, right? Because if n is bigger than n0, that's to say 1 over n will be smaller than 1 over n0, correct? So this sequence is monotonically decreasing. Which is very easy, makes the problem with limits very easy. If a series is monotonically decreasing, once it enters this interval smaller than y, it's going to keep being smaller than y from there on. I don't have to worry what happens after n0 that much, because if it happens at n0, it's going to happen after n0 too. How many people follow me here? If I have decreasing series, if something happens like it's smaller than some value, after that index, it's also going to be smaller than the same value. Yes, question? No? All right. So how do we find n0? Now, this finding n0, there is an n0, I just have to put my hands on it. When it says there is something, all I have to do is to show it, right? It doesn't matter how I found it. What n0 I need, now I have to solve this equation kind of backwards, right? 1 over n0 has to be smaller than y. Then how do I get n0 out of here? N0 has to be bigger than 1 over y. So now n0 is a natural number. So what natural number should I pick? The ceiling of 1 over y. To make it natural. So that you can see this is a scrap. I don't need to show this as long as I put my hands on n0 and then work it out. This is called backwards reasoning. Most people call it scrap paper. Like, this is how I found it, but I don't need to show how I found it. I only need to show that this n0 is the right one that I need to satisfy my problem. So I think this whole ideas here might require you to go back to high school and calculus and remind yourself of those things. That's fine, you can do that. The real question that we had last time on the board, I don't know if anyone solved it, was, can this definition of limit still stands and be correct if I start swapping those quantifiers? Right. So the definition was there is an x, right? That's the global x. Where is it? Here, right? There is an x. So there is an x such that for every y, there is an n0, and every n bigger than n0, something happens. So how many quantifiers are here? 4 quantifiers I need for this limit definition. The question that I posted last time is, can I make the definition work mathematically correct if I start swapping those quantifiers? Suppose I say, for every y positive, there is an x, and there is an n0, such that for every n bigger than n0, I have that property, which is an minus x is smaller than y. That's the same property, right? It's the same exact property. The difference between this statement and this statement is where I swapped the x and y. So now, in this statement, x is global. There is an x means it doesn't depend on anything. In this statement, x is not global, right? X depends on y. You can pick for every y an x. So x depends on y. In here, x is global, meaning it doesn't depend on anything. What we call in mathematics, it's a constant, right? We have a constant that never changes. So my question for you was, I still don't want to solve it, but I want you to solve it. I'm going to push into this thing. Is this a correct definition of the limit? If the sequence an satisfies this property instead of that property, can we conclude that the sequence is still convergent to the limit x? So what I like to show is that from this property, I can still say limit when n goes to infinity of an is x. Although this x it's a little bit funny, I don't have an x, because in this statement, x is not global, right? In here I could say the limit is x. Which x? Well, that global x, right? If there is an x with such and such property, that global x is the limit. In here, I don't have a global x. I say, well, for every y there's an x. If there's different x's for different y's, which is definitely possible, the way it's formulated, I actually don't have a limit value. So I can't state this mathematically. I'm going to say there exists a limit. I don't know which one it is. Is there a limit? So this is an honors question that's optional, which is, if I modify the statement, can you prove there is a limit, or can you find me a counterexample where the premise holds, but there is no limit? Because I changed the premise. It's not the limit definition. So now with this change, is it still true that there is a limit, or it is the case now that you can find a counterexample where the premise holds, but the sequence is not converted? I still want to leave this for now as an exercise, but make no mistake, we're going to have to get to the answer of this thing. So my moral here of the story is the order of the quantifiers is absolutely critical to what you mean. Changing the order may change the meaning. The other thing that we need to worry about to do my purpose for today is to walk you through a bunch of proofs. Some of them will be very simple, will go very fast, and some of them will not be so simple. We need to spend some time on them. But before I do that, I need the quantifiers, and I need you to absolutely understand how those quantifiers work. And the other thing that I need is the implication. Let's call it P. I want to make here a table, Q, that you already seen. P implies Q, right? That's a truth table. 0, 0, 0, 1, 1, 0, 1, 1. And I want another one, which is, this is the implication, right here. And this is not Q, implies not P. We're going to call this contrapositive. Implication sometimes is called positive. And we need another one, which is called converse or reverse. So we need to build this table. I'm pretty sure we already discussed briefly a recitation of this. When is P implies Q false? There's only one case when the implication is false. Which one is that? Somebody else. When is the implication false? Yes?
When P is true.
Which is the third case? Right. So that's the false case. The rest of it is true. This is something that some students, even the very smart ones, sometimes when you hear it for the first time, you gotta make an effort to wrap your head around it. Wait a minute. You're telling me 0 implies 1 is correct? Like false implies true. Is that a true statement? Yes. We can disagree philosophically about this. You may say, hey, that's not philosophically right. Doesn't wrap my mind. Other people can say, no, that's right. It makes sense to me. It doesn't matter. It's a convention, so it's true. 0 implies everything. Now, this is another implication, just written backwards. When is this one false? Again, when this is true implies false, right? Because an implication, it's false only in one case. Now, what does it mean for this to be true? Q is false. And for this to be false, P is true. So which line is that? When Q is false to make this true, and P is true to make it false. Which line is it? Same line? I'm really asking mechanically here, like try all possibilities, which line gives me true implies false? It's the same line, right? The other ones, because an implication, except for the case true implies false, which we know is not correct, not true, the other ones must be 1, right? And what's the converse? Everybody can remind me of that? What's the converse? Or the reverse? Or the other way?
Q implies P.
Louder?
Q implies P.
Q implies P, right? When is that false? When is Q implies P false? Q must be Again, the implication is false in only one case. When the premise is true and the conclusion, that's what after the arrow is the conclusion. So it's got to be true implies false. When is now, what line is that? True implies false.
The second line.
That's the second one, right? So this is, because an implication, every other case must be true. So I want to make two immediate observations from this table. What are the two observations? What can we see without thinking too much? It's a truth table. So can we say the contrapositive, if logically equivalent with the direct or the implication? Sometimes this is called the direct. Is that true? These two columns are the same, so they're logically equivalent. When one is true, the other one is true. When one is false, the other one is false. And what's the other immediate observation? The converse is not logically equivalent with the implication. Most mistakes on logic problems in this class are because people miss these two obvious things. Because we don't have that difficult logic problems to really requires a lot of creativity. Most of the mistakes would be like, I proved the converse when I was supposed to prove the direct. And I was confused and I wasn't sure and I leave it at that. And in fact, I proved it the other way. Now it's especially confusing when they are logically equivalent. Because some problems require you to say if and only if this is that. That means both the implication and the converse are correct. So you prove one of them, but you get lost in which one did I prove? Did I prove the direct or the converse? So most of the problem, logic losing points would be in here. So let me give you another example of a predicate here. That was, I thought it's funny from the regular section. And then we'll go to do some proofs. Aristotle stated the following. All men are mortal. And Socrates, this is a very famous classical scientist, is a man. Therefore, or thus, or then, that means in mathematics, it means implies. Every one of these words means that from this premise, so I just want to show this example because it's funny. I saw in the regular notes. Here's how I can translate that into predicate thinking. I say whatever X is belongs to the man set. M is the set of men. Set of men. Whatever X is in that set, I can write mortal of X, where mortal of X means what? It's a predicate. Let me write it capitals. Mortal. I said X is true if X is a man. And false if X is not this now stating the same thing as this? Every X that's a man is mortal. It's saying the same thing? Okay. Now how do I say Socrates is a man? Socrates belongs to the set M, therefore mortal of Socrates applies. That's how I write this implication, right? Socrates is now a mortal person. How about, now that I have all that, this is just a translation of English logically into some math predicates and quantifiers. How about if I say, okay, if this is the statement, yes?
Wouldn't the predicate for like moral on the right, wouldn't that be dealing with whether they're moral or not whether they're a man? Does that make sense? I'm asking?
Yes, but the way we defined it, so we take the statement, so we try to translate what those people wrote. All men are mortal. So what you're saying is, I don't need men in here, I need what?
Moral.
Mortal means what? I mean,
They don't.
in English.
They die.
So his objection is, all men are mortal. You okay with the statement here, right? All men, mortal of X equal true. He has a problem with the way I define mortal. Right? And is that, what do you guys think? Is that the correct definition of mortal or not?
Not necessarily, because X could be an animal. And that goes
We are so small.
Okay. So
But it will still.
how do we write it then? Can die? That better? And if X is false, cannot die. Is that now?
Makes more sense to me.
All right. But we leave it as vague. What can it not die? That's another philosophical question, right? I mean, we can argue everything dies in the end, right? Okay, but I agree with the observation. That's a better definition of mortal. Perhaps it's going to help us what I want to say next. Aristotle didn't mention women in his statement. So what if we bring that into the play? Who's W? Instead of women. So now, I think according to him, he implies to say mortal should apply to women too, right? Not just to men. Can we state every X in W, we have mortal of X? I should write it here. Every X, a woman, instead W, then we have mortal of X. Is that a true statement? That is a true statement according to our own Virgil's intuition. But is it a true statement according to Aristotle? No. Who knows what's in his mind when he said that? Doesn't matter. When I translate English statements from a problem that's given to me with candies and toys and men and women and whatever else, make sure you translate exactly that statement into math, not what you think is correct. You might think, hey, candies are more valuable than toys. Who cares? That's not what the problem is saying, right? So you gotta be careful when you take those English statements and you make math out of them. Do not translate less or more. This might be true, but we don't know. How about we define another predicate, human? Human and X is true if what? How do we write this one? Somebody else. How do we define? X has to be men and woman, or men or woman? How do I write that? M union W, is that right? And false if X is not M and X is not O, right? How about this? Okay, so I have now another predicate. Can I say for every X without specifying what X is? X can be any item in the world whatsoever, any element. Can I write this implication? Human of X implies mortal of X? So again, according to our knowledge and understanding of things, I think this is true, right? Any human is mortal. Is that right? How many people with me here? Okay, this I know this is not a matter of intellect, it's just a matter of whether you're paying attention or not. I see some people on laptops. I'm assuming they don't study Aristotle on the laptop, so if you don't pay attention, I understand that. But if you do, I think this is easy to follow. But not, is this according to Aristotle true or according to me true? Which one is it? How about the other way? Mortal of X implies human. Is this true? I'm really not in the mood to give answers today. I'm in the mood to ask questions. Sorry. So this is the kind of questions you're going to have in the next homework and quiz. Hey, wait a minute. Which one is mortal and which one is human and which one is according to the quiz statement? Okay? If it doesn't specify, if it asks you for your own knowledge, then fine, you put your own knowledge. But the way we define if X can die, X cannot die, is this true? Any mortal must be a human? How about a bird or a fish or anything, other animal? Can it die? Yes. Is it a human? Yes implies no is what kind of statement? False. Okay. So you're going to need a little recap before quiz and exams. This stuff, it's easy intellectually speaking. The hard part is making sure you get exact definitions and equivalences. So I'm ready to do some proofs, and you have to prove this limit very soon. So let's start with some simple ones, and we see how far we go, and what we can't do today, we'll do next time. I guess we're gonna need another table here very soon. What do I have? So problem 1. X odd. When I say odd, what kind of X I'm talking about? If I don't say anything, I just say X odd. What is X? What kind of number? Integer, right? When I say odd, I cannot possibly talk about humans or items or real numbers, right? I have to implicitly, odd is a set of integers that have a certain property, means x cubed is odd. I could write this in English. If x is a natural odd number, then x cubed is also a natural integer number. So I could write that. If x is an odd integer, then x times x times x is also an odd integer. I won't spend much time into translating English into math, but that's what a lot of the notes for the regular sections are. How to take an English statement, translate it into math. So if you feel like struggling with that sort of thing, you should read the notes that we put online or the book. There's a lot of practice questions writing there. I'll just put it straight into math, focusing on the proof into it. How do we prove this thing? Somebody. If I want to prove this statement, how do I do it?
Take some odd number, 2k plus 1.
X is odd means X is
2k plus 1.
2k plus 1 means X cubed is,
2k plus 1 times 2k plus 1 times 2k plus 1.
let's say cube, which means X cubed is, how much is 2k plus 1 at the power of 3? 8k, I hear some rumors in the back. 8k cubed, what else? 4k squared plus, no? 4k, maybe? How much is it?
12.
This is 12k squared? 12k squared. Plus 6k? Plus 1, okay? So that is how much? I need to show it's odd. So if I want to show something it's odd, I need to bring it to what sort of form? 2 times something plus or minus 1, right? So how do I take this and make it 2 times something? 4k cubed, 6k squared, 2k plus 1, and then I say this is odd now because it's, I could write it here as 2 times something plus 1 to make it more clear what I mean. 2 times something plus 1 is odd. This proof, it's called a direct proof. I start to the premise, odd, dang, 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 implications, boom, I reach the conclusion. We can be written more succinct than this. You know, you can skip some of the steps, so to speak, if it's clear where it goes. So, you know, if you get, for example, from here to here directly, and then as long as every step is clear for the reader, that's fine. So this is direct proof. Can I make, what will be a contradiction proof? How would that look like? If, in this case, I want to make a contradiction proof. Yes?
Assume for contradictions x cubed.
Assume, say, hypothetically, that x cubed is odd, meaning it's 2k plus 1, right? Even. Why even? Because it's not odd, that will imply x cubed must be even. So that implies it's some 2k. And then I need to build up implications here. That's your homework. To reach a contradiction. A contradiction can be reached against what statement? If I am to reach a contradiction, what do I have to contradict? X equal odd, right? So I need to build a contradiction here that's coming from what do I need to prove in order to get a contradiction. I already know x is odd, and if I want a contradiction, what do I need to prove here? X even or not odd. Right? We know already that all the integers are either odd or even. So what steps do I need in here to get to the contradiction that I want? I have to get to x equal even, right? Yes.
We have a set of steps that shows x is, or x cubed is odd, which contradicts x cubed is even.
There are many ways to go around this, and this is actually much harder than this proof. You still have to go backwards in the other way. The point is, if you want a contradiction, the way you start, you say, let's assume hypothetically the conclusion is false. That's what we did here. And then skip a bunch of steps and say, where do I want to go with this thing? In order to get my contradiction, I have to contradict the premise. The premise is x is odd, so I need to contradict that, which means x is even. So now I know what I have to prove from where I started my hypothesis, go to x equal even. Try to figure out, see if you get those steps to work. Let me do another one. Very similar problem to I'm gonna skip this one here. If m and n are squares, what's a square? What's a square? Somebody else. What's a square?
Number raised to the second power.
Number raised to what power? But what number?
And then
It has to be an integer, right? So let's write down what the square is. Square is an x squared with x integer. That's what the square is. It's something, an integer, multiplied with itself. If m and n are squares, m times n is also a square. So I could write this in predicate form, right? I define the predicate square, and then how do I define that? Square predicate, square of y is true if there is an x in z such that y equals x squared, and false if whatever x in z, what? What's the negation of this statement? If there is an x in z, x squared equal y, that's true. If for every x in z, y is not x squared, then that's false. This is the complement of the other statement. Either there is an x for which y is x squared, or there is no x for which y is x squared. That's my predicate. How do I write this now with predicates? If square of m and square of n, then that's the implication, what? Square of m n. Like I said, this is just a way to make things more complicated. It doesn't add any mathematical ability. It just translates the text into predicate form. Now, is this true? That's not a proof. That's just me playing around with these statements instead of writing in English, writing with math. Predicates. By the way, I'm trying to avoid for myself when I solve a problem this predicate form. I found it that it adds formalism and diminishes my ability to think. So whenever possible, if the problem doesn't state use a predicate, I'm not using predicates because that's a personal preference. I like things written this way. This way I can understand better what's going on. If somebody starts with squared and all that, I'm like, what is this? This looks like a function to me. What kind of function is that? I get lost. So I'm just telling you my personal preference. I don't like things that are more formal than minimum necessary. I like formalism only when it allows me to think and allows me to build up the pipeline of a proof. But I don't like additional formalism because that clouds the things and then I get lost. You might like more formalism than me, and that's fine. But I like things written this way. That seems more simple, more easy to think about. Now, how do we prove this thing? Is it direct proof? Okay, direct. How do we do it? If m is, which means x squared, and n is y squared, then mn is what? X squared times y squared, which is xy squared, which is a square. Done. Again, as far as this class go, like in math, if you go to the math department or go to the PhD, you may need to add some details here. But in this class, we only care about the core implication that proves the problem. This would be full credit as far as this class goes. If you write this on an exam for this problem, maximum number of points. How about another one? this is the absolute value. How much is the absolute value of a number? Is the number itself if is positive and is minus the number if it's negative, right? That's the absolute value. So that's problem 3. Prove that the absolute value of x times y is the absolute value of x times the absolute value of y. What are x and y here? Real numbers. Can somebody do this proof for me? I know you probably know this, the mathematical phenomena here. You should know this, that the absolute value of a product is the product of the absolute values. But how do we prove it? How do we show it's true? This is something that some people have difficulty about, especially computer scientists. Why do I need to prove something if it's so obviously true, right? I mean, if I know for a fact it's true, I can guarantee with my life it's true, right? I put my money on it. Why do I need to prove it? There's a distinction between what I know for certain is true according to my certainty, ability, my brain works in a certain way, it's how I grew up, whatever, and what mathematically can be proven, or what you can prove. So that's not the same thing. Even if you are certain about something, it doesn't mean that's proven just because you're certain. So how do we do this? Somebody else. Yes?
Do we go through all the cases?
The easiest way to do this one, even though it's obvious, is actually to break it into cases. How many cases are there? So this is proof by cases. I would like you guys to write cases, direct, contradiction, induction, counting, whatever the proof method that you use, it's useful to see it here. I'm proving by cases. So now, what are my cases? X could be positive, y could be positive. In each case, x, y is positive. And in each case, the absolute value of x is what? X. The absolute value of y is y. The absolute value of xy is xy. Is xy checking to be x times y? Yes. What's another case? Positive, negative. So xy is negative, right? X, absolute value of x is still x. Absolute value of y is minus y. Absolute value of xy is minus xy. If xy is negative, its absolute value is minus xy, right? Well, is that true? Can I say I'm adding the equality here too? Can I say equality is in both cases? If I have 0, I can treat it either as 0 or minus 0, and that's okay. It's not the correct mathematical definition. This is the case where we computer scientists, we say, it's okay. You know, it doesn't violate the problem, right? It's just the definition includes 0 on both sides, but they're both 0. So it's not an incorrect or inconsistent definition. It helps me here when I say x, y is less than or equal to 0, then xy absolute value is minus xy. How about the other case? Negative, positive. What is that? xy is negative, absolute value of x, minus x, absolute value of y, y, minus xy. Is it true that minus xy is x times minus y in here? Check, check, check. Is it minus xy minus x times y? And that's the last case. Negative, negative. xy is positive. X, absolute value of x is minus x. Absolute value of y is minus y. Absolute value of xy is somebody? xy. Is it true that xy is minus x times minus y? So instead of check, 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 better to write what actually happened. X times y equal xy, x times minus y equals minus xy, minus x times y is minus xy, and minus x times minus y is xy. So now all check out. Now this is not the formal proof. In the math department, you're gonna get in trouble if you write this down, right? Because you have to say there are 4 cases. Case 1, da 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 da. Therefore, blah 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 blah. Check that, right? Case number 2, da 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 da. In computer science, just put this table, you're done. Okay? Say there are 4 cases. Here they are. Check 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 check. Full credit. Okay? But if you do a PhD or you take some classes in math, you're gonna have to write more. In here, we only go for the core idea of the proofs. Okay, let's keep going. Here's another one. If x is odd, there is a k integer such that x is the difference between k plus 1 squared minus k squared. So it says every odd number. Let's write that in English. How do we write this in English? That's problem 4. Every odd integer is the difference between 2 consecutive squares. That's what that be in English. Every odd integer could be written as difference of 2 consecutive squares. Consecutive because k plus 1 and k. By the way, a lot of you made this mistake in the quiz, where it says here's an odd, here's an even number, not related. The odd is 2k plus 1, the even is 2k. Boom, now they are related because it's the same k. Remember when we did this in class? If I relate the k plus 1 with k, it has to be something in the statement that tells me to relate them, like the word consecutive. If I just say here's an even number and an odd number, can't be necessarily 2k and 2k plus 1. Because I didn't say they're consecutive numbers. They could be 7 and 3. And now there's 2k and 2m plus 1. Right? A lot of you made this mistake when you talk about the generic odd and the generic even number. You call them both 2k and 2k plus 1. And that's incorrect. Because they're not necessarily related by that k. They're not that close to each other. In here they are. I put this k plus 1 and k on purpose. Now how do I do this? How do I make this proof? Yes?
Did you do induction?
I am not allowed to do induction. Yeah, I could do induction, yes. How would I do induction? If it's true for some odd number, then I'd have to prove it's true for the next odd number, right? So we'll do that when we get to induction, but now I don't want to do induction. What can I do? Yes? Direct proof? I think you have an idea to say, let's manipulate the run-high side, let's see what actually that is, right? So before I even start the proof, I'm going to say scrap paper in here. I want to see what that right side is actually. What is the right side? K plus 1 squared minus k squared. How much is that? That's 2k plus 1. Aha. So the statement is now rephrased. Every x odd, x is 2k plus 1, right? That's what the statement actually saying, because the difference between this and that is always 2k plus 1. Remember, those are related. They're not a different k. I didn't make a mistake here. They say consecutive, so they have to be consecutive. So now that I know this stuff, how can I make a direct proof?
On the right hand side, so k plus 1.
If x is odd, then means x is 2k plus 1, which is k squared plus 2k plus 1 minus k squared. Now, if I would know this, that would be a very creative step. Somebody may look at this and say, hey, how did you come up with this magic here, right? I mean, it's 2k plus 1, there it is. I added the k squared and subtracted the k squared. And it's going to check out, of course, because this is now k plus 1 squared minus k squared. But somebody might look and say, how did you know to add k squared to it? How did I know? How did you know? I did the scrap thing, and I say, how much is k plus 1 squared minus k squared? That's the 2k plus 1. So when I saw this 2k plus 1, I was like, aha, let's just call x 2k plus 1. I already know, maybe I should have said here, k squared plus 2k plus 1 minus k squared. So how did I know I need to add and subtract the k squared to get what I wanted? I did it because I first did a derivation on the right-hand side to see what is this that I need to get to. I knew 2k plus 1 can be the difference of two consecutive squares. So there's still a direct proof, but I needed some backwards reasoning first to see where I need to go with it. Okay. Let's do another one. Problem 5. If 8 does not divide n squared minus 1, then n is even. If I write this, let's make sure everybody follows. What is n in here? For this to make sense. What item is n if I don't say nothing else? When I use this division, integer division, n squared must be an integer, and therefore n must be an integer. So if I don't say anything else in here, n is an integer. Now, perhaps the problem would be more clear if it says whatever n integer, da da da. But in some problems you don't know whose n is. It's implicit from the statement. If it says odd or even, or talk about integer divisibility or modulo arithmetic or something like that, it's an integer. If it just talks about a quantity, generic quantity, it's probably a real number. So is this true? If 8 does not divide, this divides means integer division, right? This 8 divides a number when the number is a multiple of 8, and it does not divide a number when the number is not a multiple of 8. Right? So let's write this as a legend. What does 8 divide anything means? X must be of the form AK. So this statement can be read in English as if n squared minus 1 is not of the form 8k, because it says not division, then n must be even, or else n is not odd. So how do we prove this? Yes?
We can prove the contrapositive.
Contrapositive. What would be the contrapositive?
If n is odd, then we divide it.
Which we already show. We had a table in there somewhere that says contrapositive. Did we delete the table? Oh, you still have it. What's the contrapositive in here? I want it with not signs.
So if
Not what?
Not and even.
Implies?
Not like.
So now, if I apply the nots to these statements, what is not and even means? And odd. And what is not true that 8 does not divide n squared minus 1? What does that mean? Nice. Now what? I mean, that's not a proof. It's just saying, instead of doing the direct implication, we can prove the contrapositive, we know that for every mathematical statement they are equivalent. So if you prove this one, the direct is true. Somebody else. How do I prove this one?
You set n to 2a plus 1.
Who's talking? Okay. So how do I do a direct proof here?
Yeah.
Okay, so n odd is 2k plus 1, right?
Yeah.
And then n squared minus 1 is what? If this is, I'm assuming you're going to do a calculation here.
Yeah.
N squared is, so that's 2k plus 1 squared minus 1. How much is that? 4k squared plus 4k plus 1 minus 1.
Yes.
So how much is that? 4k squared plus 4k, because these plus 1 and minus 1 go away. And now, according to the contrapositive, I need to prove 8 divides that.
Right.
So why is, to show, the easiest way to show 8 divides something is to put it in the form 8 times something, although that's not in that form 8 times something yet.
Could you do equals 8 parentheses 1/2 k squared?
K squared plus k divided by 2?
Yeah.
Because to make it the 8 in front, I need to do something by 2. Because I get the 4. K squared plus squared has to divide by 2 now. Now, when I say 8 times something, that something has to be an integer. This is not trivially an integer. Is it? I mean, it may be an integer. I'm just saying, by the look of it, it's not always an integer, right? If it's 8 times a plus b times c minus d, you can say everything is integer there. That's an integer I don't have to worry about. But this is not that way. This k squared and k, they are integers, but division by 2 can cause problems. I know, somebody else. Sorry. Is this an integer, k squared by k? K squared plus k divided by 2? Yes.
So you can just say that that's the same thing as k times k plus 1.
Like that? 8 is 8, 2 is 2, and what he did is wrote k times k plus 1 times that. And now?
And then those are two consecutive integers, so one of those is going to be equal.
So his argument here is this gotta be an integer. Between k and k plus 1, consecutive numbers. One of them must be even. Therefore, that even one ensures divisibility by 2 works out to still be an integer. So how do I further write that down nicely? I mean, I said it, but now what? Like, you leave it like that, lose points. What do I write? I can do cases from here, right? Who said cases last time? I can do cases and then say, oh, okay, if k is even, da da da, if k is odd, da da da. Or can I write it 8 times an even times odd divided by 2? I make the case that one of them is even, the other one is odd. And then I say even by 2, that's an integer. So I'm going to write it as 8 times an integer times an odd number. And now that is 8k. I shouldn't use the same k here because I already have a k. That's a multiple of 8. That sort of writing, again, is at the border between computer science and math. In this class, this is fine. As long as we can tell how you thought about it, as long as me, the reader or the grader, look at his paper and say, he figured out that between k and k plus 1, one is odd, one is even, and the even one ensures the proper divisibility. If I can rebuild that reasoning, if the writing is clear enough, that's fine. In the math department, it's not.
So would we need to prove that, like, of two consecutive integers, one is even and one is odd? Like, would we need to do that?
That's assumed proof. I think we talked about it. Between any two consecutive integers, we already said that after even comes an odd and after an odd comes an even. Now, you could prove separately, so I could have proven before that k times k plus 1 by 2 is an integer. So proof, maybe I proved that as a separate statement before this, like a lemma. And then I don't have to worry. Once I get here, it's a times an integer because I already proven that. Hands up, who's with me? Good. Good. Okay, problem number 6. X squared plus 6x plus 8 is odd. Implies x is odd. True or false? Okay, how do we prove it? Let's prove it quick. What? I can do a proof by contradiction. Let me try a direct one first. X squared plus 6x plus 8 is x squared plus even. Right? Because 6x is even, and 8 is even. So that means x squared plus even plus even is even. So now I know that is an odd, because that's what the problem is saying. So from here, if I move the even on the other side, I get x squared is odd minus even, which is odd minus even is odd. So now I've got x squared is an odd number, but I need x being an odd number. Now what?
X squared has to be either an odd times an odd or an even times an even.
Cases.
Yeah.
So now somebody says cases. Continue with cases. Anybody has a different idea what can I do here other than taking cases? Is there a way to obtain x out of x squared?
Square root of an odd number.
But square root doesn't, I need to know that the square root of even is even and may not even integer sometimes, I don't know. Maybe do cases, that's up to you guys to continue. That's a direct one. And if I do contradiction, you guys can see here. How do I prove that by contradiction? Assume x equal even, right? Meaning not odd. That implies x is 2k. So now I calculate this formula, x squared plus 6x plus 8 is 4k squared plus 12k plus 8 equal even plus even plus even equal even. That is a contradiction, right? Contradicts the fact that x squared plus 6x plus 8 is odd. So now my contradiction must come because of my assumption was wrong. So that means x is odd. That's a proof by contradiction. That says, let's assume the conclusion is false, right? It's not odd, it's even, and then we show contradiction. Now, the contrapositive and the proof by contradiction, they are the same thing, right? The contrapositive in here, it's what? Not x odd implies not x squared plus 6, 8 plus 8 odd. So that's effectively saying x even implies x squared plus 6x plus 8 even. Which is what we prove to get to contradiction. So this proof by contradiction, or the contrapositive, is pretty much the same exact steps. Yes?
For the first one where you did the direct proof,
I get to x squared equal odd in a direct proof.
right, can you go to x squared equals odd, so that means it has to be 2x plus 1 squared? Oh no, that's the other way.
Right, so let's see how that works out. What she's saying is, let's continue the direct proof from here. X squared is 2k plus 1, right? It's odd. And then
Could you,
I need a way to get x out of here, right? Because my purpose is to prove x is odd, not x squared. And I can do cases, take cases and see which one works out. Is there a direct way to get x out of here? That's my question. Maybe not. There's a bunch of those like this. Here's one that we I think we did informally at the recitation. Let's do it more formally now. If n equal AB, then A is smaller than square root of n, or B is smaller than square root of n. The condition here are for n, A, B to be all positive. They could be real numbers. Doesn't have to be integers, but they have to be positive for this to work out. Is this a true statement? Remember when we did factorization that if you check for numbers prime, you go up to the square root, because a product, A times B, one of them has to be at most the square root. You can't have two numbers bigger than square root. Okay? So how do we prove this? What is the technique here to make this proof work? Yes?
Contradiction.
Contradiction. How? Assume. How do I contradict or this and that? Not A is smaller than square root of n or B. So this means what? If I negate the conclusion, right? Premise, conclusion. If I negate the conclusion, then what? What do I get? How does not distribute over this whole thing? A is bigger than square root of n, and B is bigger than square root of n, right? Can everybody see that? Not applied to this means A bigger than the square root of n. Or becomes an n, because that's how the Morgan law says not distributes over the or. That is the other side, not B smaller or equal than square root of n. So now if both are bigger than square root of n, what do I do to get my contradiction? I make the product, right? A times B is bigger than square root of n times square root of n, which is n. That's a contradiction. It's useful sometimes to say contradicts exactly what statement. It contradicts the fact that AB is supposed to be equal with n. It can't be bigger than n. Right? AB can be at the same time bigger than n and n. Right? Therefore, I get my conclusion. All right. How about one that's a little bit more interesting? That is what problem number 6. Here's problem number 7. Square root of 3 is not a rational number. Now we all know square root of 3 is a number, right? There is a number, real number, that multiply with itself gives 3. How much is it approximately? 1.7 something, right? So there is a real number. Now, is that real number a rational? What is a rational? Now rational is a fraction of a by b, where both a and b are integers, right? So what is this statement actually saying? So that's a translation. Here's another translation. Wherever you pick a, b integers, for any a and b integers, anywhere you pick them, then what? Square root of 3 is not a divided by b. You cannot pick two integer values that when you make the division, you get square root of 3. Not possible. How we prove that? Anybody else wants to try a proof here? That is not a hard proof, but it's a little bit more difficult than the ones we've seen so far. Proof by contradiction. Now there is a proof by contradiction that it's more accessible but longer and messy, so I'm not going to do that one. That's in the notes. I'm going to do something that involves a little bit of number theory, but the number theory that you already know. So I'm not going to need to add number theory to it. The reason they do this other proof is that they totally want to avoid number theory, and then it's more steps. But with this, it will be quick. Just we're going to need something from number theory to do it, okay? So how do we prove by contradiction? Assume what? How do we negate this statement? There is an a and b integers such that square root of 3 is a by b. Right? Then what? Remember, I have to get to a contradiction. I have to contradict something. Do I have something to contradict? A and b are integers, right? Now, before, when we talk about contradiction, the contradiction was pretty obvious what's supposed to be, right? The problem says something in the premise, you know, Virgil is rich, blah, blah, blah. You start with some assumption. What do you have to prove to get a contradiction? Virgil is not rich. Now, the only thing I've got is the square root of 3 in the premise. I got nothing else. So I can't really contradict the square root of 3 existence of it, because I can't do that. I have to contradict something else, right? So what are we going to contradict?
Would you say that a equals the square root of 3 times b, and since square root of 3 is not a rational number, then...
Right. There's some manipulation steps. You're talking about 3 equal a squared by b squared, right? And then keep going from here. But what's my contradiction going to come from? I have to end up in a place that says this directly contradicts something else. What am I going to contradict?
That A or B is not an energy.
This I'm going to contradict. This is not given in the statement per se. It's just something that I'm assuming, right? And that's still a valid contradiction. It's not just obviously negating the premise. So let's see if we get there. 3 equal a squared times b squared. Now then what? What do I do next? What? A squared is 3b squared. Okay. Then? I mean, everybody agrees with this, right? Now I have to contradict something. What? I don't see a contradiction yet. Yes.
So if A is a square, it must have all of its prime factors twice.
Okay, that's the number theory property we need. That everybody knows that, but we didn't get to number theory yet. We'll get there in about after the midterm. So the reason this doesn't work, the reason it's a contradiction, is because a squared, all primes are at even power. There is something in number theory that says every number can be decomposed into primes. How many people know that? Even if you don't know it in number theory, don't you know that integers can be decomposed into a factorization of primes? Right. So here are the primes. Prime 1 at some power, alpha 1, prime 2 at alpha 2, times pk at alpha k. That's primes. But then a squared is who? If I square this whole thing, what do I get? p1 at what power? 2 alpha 1 times p2 at what power? 2 alpha 2 times pk at what power? 2 alpha k, right? Because when you square a number, you make all the powers double. So if this was, for example, a is 3 times 5 times 7 squared, who's going to be a squared? 3 squared times 5 squared times 7 to the 4th, right? I don't even have to calculate the actual value. I know that's going to happen. So all primes are at even power. How about in b squared? Same thing. All primes have even power. So now if you pick the prime that you care about, exactly 3, these 3, that prime is going to be prime 3 at an even power equal 3 times 3 at even power. Right? Because primes don't interfere to each other via multiplication, right? The 3's as the primes have nothing to do with the 5's and the 7's and all the other primes in the multiplication. The 3's in here have to correspond to the 3's in here. In other words, if this side has 25 3's, this side also has to have 25 3's. No other prime factor can substitute the 3 in here. How many people with me on that? What I just said is that if two numbers are equal, x equal y, the number of 3's in this side has to be the number of 3's in this side. Because no other prime factor can substitute for the missing 3's. That's the same with every prime. The number of 5's in here has to be the number of 5's in here, 7's, 11's, right? Prime factors only come from multiplying them with themselves. So this 3 has to be an even because it's a squared. This 3 has to be at an even power because it's b squared. But there's another 3 in here. So then I've got, if the exponents have to be equal, even is even plus 1. Right? 3 at 1. Is that a contradiction? Here's a problem, honors problem, that's an exercise. I'm not going to do it here. Problem 7 prime. If n is a natural number, square root of n is either a natural number, as in square root of 16. How much is that? 4. Or square root of n is not a rational number. So there's nothing in between. Those square roots of natural numbers are of two kinds. Either you get an exact whole number, as in square root of 16. And if that doesn't happen, then you get an irrational number. You can't get a rational, as in 23.65, out of a square root of an integer. You either get a whole number or an irrational number. Now that's a little harder. It's still playing with prime factors, but it's saying much more than this. It's saying any square root of a natural, it's either a natural or an irrational. Try to do this by tomorrow at recitation, yes.
Shouldn't that be an XOR?
What?
That needs to be an XOR.
This?
Instead of or, should that be an XOR? Or is it not that?
Saying it's either that or that.
Oh, yeah.
My English wrong? Here's one that I want to do here. An existence proof. kind of problems, which are very rare in math because they're not useful at all, it says, show me an example of that property. These are useful when you're actually trying to prove there is no such thing. If you can prove such an example, you typically are on the path of finding a counterexample to some proof. But nevertheless, existence means show me an example. Show me an x that's a sum of cubes, that it's in two ways of sum of cubes, right? So here's the proof. That's existence proof. So it's just finding the example. 1729 is 1 cube plus 12 cube. And 1729, the same value, is 9 cube plus 10 cube. It's a sum of cubes in two different ways. Now, I only have to verify the math to make sure it works. You can do that. Now, an existence doesn't require me to show how I've got 1729. Some of you in the quiz, some of you had a problem with something that was disproof. You know, you just have to show an example for A and B with some property in the quiz. Remember, the sections on Thursdays have a, and they spend a lot of time trying to explain me why that is possible and how to find a counterexample. We don't need none of that. We only need the counterexample. And by the way, if you wrote all the theory that concludes there must be a counterexample, but you didn't put it there, you lost some points. Okay? You have to put the counterexample. So in these problems, you gotta put your hands on it. I don't have to explain where I've got it. I just have to show that it's the sum of two cubes. You can verify with the calculator that this is true. That is done. Now, there's a much more interesting problem, honor section problem. Find me the numbers that are sum of two cubes in two different ways. Can you find me all of them? Say all of them less than 1,000,000. How do you go by and solve the equation x cubed plus y cubed? That's a different problem. Is z cubed plus t cubed. What are the numbers that can be written in two ways as sum of cubes? So find all a's less than 1,000,000 or 100,000,000 that satisfy this problem. Now that's a far more interesting question.
If hypothetically something could be expressed in 3 ways, does that count?
Yeah. So it's not exactly 2 ways, it's 2 or more. But again, for the basic problem, we just need to show an example. An example proves exists x with some property. Here's some other problems that I'm going to prove here. This was problem number 8. Here's problem 9. I'm going to prove 1 equal 2, okay? That's my next proof. It's written here. I didn't read this proof, so I'm just going to, you know. I'm going to side with let if a equal b, 2 integers. That's easy to get, 2 integers that are equal. I'm honestly didn't have time to read all these notes, so I'm just going to write what's in here. Let's see where the proof goes, right? I guess they're multiplying with a in here. What's happening here? Subtract big square out of it, both sides. So this is a formula that I hope you guys know. A minus b times a plus b, it's a squared minus b squared. If you don't believe it, you can just open the parentheses and see what happens. Right? And this is common factor b, right? So now it says a plus b equal b. I'm assuming in here is a division by a minus b. Because if I take away a minus b, I get a plus b equal b, right? And then subtract the b. What is it? No, wait. Don't subtract the b. Then I use the fact that a equal b, I guess. 2b equal b. Right? Because a equal b, right? So this is b plus b. b plus b equal b. So now 2b equal b, then I divide by b. 2 equal 1. You laughing at me or at the proof? I don't know who wrote this. Is it true?
No.
Okay. I don't need an explanation right now. I need you to go home and figure out where is it wrong.
Oh, yeah. I did say that to me directly, but I was watching it.
I want to do one more before we break off. I have a very interesting one that I'll have to do on Friday, but I have a quickie one to do here. With proofs like this, you can prove anything, right? Remember Virgil is married or not married with Nicole Kidman? Easy to prove with these statements. Either way. So here's one that's a backward reasoning proof. I want to prove that 1/2 of x plus y is bigger than x times y at 1/2. Now, the problem in here is I need handles. I'm not sure where to start. That's what I want to prove. Let's assume x and y's are reals positive for simplicity, right? So how do I do this? What I want to do here is to do a backward reasoning, but keep equivalence. So I'm like, I really want my proof to go the other way. That's going to be my proof. But I don't know where to start this proof. I don't know how to go start somewhere to end up in here. That's what I want to end up. I can say here 1. This is what I want. So what am I going to do? I'm going to start derivating this formula by keeping equivalence so that wherever I get to something that I know or is true, I could reverse it and go back. So how does this look? Let's square it, right? So 1/2 x plus y bigger than xy at 1/2. If I square the whole thing, I get 1/4 x plus y squared bigger than xy. So this is by squaring. And now, I can multiply by 4. X plus y squared is bigger than 4xy. Right? I multiply by 4. And now I open parentheses, x squared plus y squared plus 2xy bigger than 4xy. So this is open parentheses here. I want to move the 4xy on the other side, so it's x squared plus y squared plus 2xy minus 4xy bigger than 0. And now I've got x squared plus y squared plus 2 minus 2xy bigger than 0, which is the same as x minus y squared bigger than 0. I think the problem states x different than y. Blah, blah, blah. Make it work. Now, do I know this is true? If x and y are different? Any square of a number that's not 0, x minus y is not 0 implies that. So what did I do? I took the what I wanted and go all the way down with it. Make sure it's reversible. All these steps, they gotta be reversible to now make a proof. Now I can read this whole derivation backward. That's my proof. I start here. From here I get here, here, here. See, so I go in opposite direction. I'm gonna prove my formula, assuming every single step was reversible. So this backwards reasoning is extremely useful, even if the steps are not reversible, to give you a hint of what do you need, where are the handles that allow you to do this. Because you're not going to guess immediately what they are before you do some derivations.
Yeah.
Let me get a camera.
I don't.
Because you end up with an algebraic statement that doesn't necessarily relate to it. You need to start that. If someone just showed you x minus y is equal to 0 implies x minus b.
Is this